Everyone. Today we are going to learn about reduction of higher order differential equations to a system of first order differential equations. So let us consider a higher order differential equation. So consider, say, mth order ordinary differential equation. Say mth derivative of y with respect to whatever is the independent variable is a function of t dependent variable and all its lower order derivatives. So first derivative, second derivative, and so on, y m minus 1 derivative. And say this differential equation of mth order is also connected with some initial conditions. That y derivatives at t naught are, say, eta of k, where k0 means y value at t naught is eta naught, first derivative value, second derivative value, and so on up to m minus 1 derivatives. The initial values are known. So to convert this mth order differential equation into a system of m first order differential equations, we consider that the dependent variable, which is y here, is taken as a new variable, say u1, and all its derivatives, which are y dash, y double dash, so on, y m minus 1 derivative, they are also taken as new variables. So y dash is considered as u2, y second derivative is u3, y4 third derivative is u4, and so on. So y m minus 1 derivative will be um. So by this consideration, it is easy to see that if I differentiate this equation one time with respect to the independent variable, then I can calculate from here y dash as u1 dash, and clearly because of the second equation, because y dash is u2, so I can substitute it on the left hand side to easily rewrite that u2 is u1 dash, or simply the first derivative of u1 is u2. Okay. Similarly, if I differentiate this second equation one time, then I can calculate y double dash as u2 dash, and immediately from third equation, because y double dash is u3, so I can define that u2 dash will be u3. Similarly, again, if I take one derivative of this, then third derivative of y will be u3 dash, and third derivative is u4, so I can easily define that u3 dash will be u4. This can be continued until I calculate u of m minus 1 derivative. Okay, so one previous term derivative, that will be equal to um, and this last equation, if I differentiate this, then I will end up with y derivative m as um dash, and y derivative m is already given by the differential equation, so I can substitute this on the right hand side to write the last equation as um dash is equal to ym, which is a function of all these variables. So a function of independent variable t, dependent variable y, and y is u1, y dash is u2, and so on, m minus first derivative, which is um. So instead of y dash, we will write u1, u2, so on, um. So by this way, we can convert the mth order differential equation into a system of m first order differential equations. Also, the initial conditions will also convert using these considered values. u1 at t naught will be y at t naught, and y at t naught is eta naught. Okay, each first order differential equation will be linked with exactly one condition. So this equation will have the condition that u1 at t naught is eta naught. Similarly, second equation will have u2 at t naught, and u2 at t naught means y dash at t naught, and y dash at t naught means eta 1. So on, this can be continued and all the conditions can be calculated. Um at t naught, so um at t naught will be the last term, which is ym minus first derivative at t naught, which is eta of m minus 1. So we'll have a system of first order differential equations along with the initial condition at for each first order equation. So this way we can easily convert any higher order differential equation into a system of first order differential equation. Let us now consider one example. So let us say we want to convert the second order differential equation into a system of first order differential equation. So let us say that the differential equation we given by this t times y double dash minus y dash plus 4t cube y is equal to 0, and this second order differential equation has two conditions, say y at 1 be 1 and y dash at 1 is 2. So let us first see that there is a second order differential equation with the coefficient of highest derivative is t. So we can rewrite this by taking y double dash, taking all other quantities to other side. So 1 by t of y dash minus 4t square of y. Okay, so taking these two terms on the right hand side and then dividing with the t. Now this second order differential equation will be converted into two first order differential equations. For this we have to choose dependent variable y as u1 and the derivative of y as u2. Clearly, if I differentiate this first equation, then I will get that u1 dash will be y dash and y dash is u2. So u1 dash will be u2. And if I differentiate the second equation, then I will calculate u2 dash equals to y double dash, and y double dash is given by this equation. Okay. So I can easily rewrite it as 1 by t of y dash, and y dash is u2 minus 4t square of y, and y is u1. So immediately I have the system of equations, and each equation will be linked to one condition. So first equation will have condition from the u1, u1 at 1. So u1 at 1 means y value at 1, and y value at 1 is 1. So u1 at 1 is 1. u2 at 1, and by definition u2 at 1 means y dash at 1, and y dash at 1 is 2. So we get this. Okay. So easily we have converted this second order differential equation into a system of first order differential equation along with the conditions. Now this system of equations can also be easily written in matrix form. If you consider that your dependent variables create a vector, say u vector is a set of dependent variables u1 and u2 in this case, okay, then derivative of this vector du by dt is derivative of each of these, so it will be equal to u1 dash and u2 dash, and u1 dash and u2 dash values are from these equations, so we can easily rewrite them as u2 1 by t u2 minus 4t square u1, and this is a column vector which can easily be written in terms of a matrix times the dependent variable u. Okay. We can easily rewrite it as a matrix times the dependent variable which is u1 u2. So you can easily see that we need the coefficients of u1 in first column and coefficients of u2 in second column. What we'll have in first equation is 0 1, and in second we will have minus 4 t square of u1 and 1 by t of u2. Basically we are trying to write this as a matrix times the u vector is u1 u2. Okay. So clearly we can define the system of first order differential equations in terms of matrix as u dash is equal to au, where a is matrix depending upon the whatever is the right hand side. Also the initial conditions can also be defined. This initial condition will easily convert into u vector value at the initial point 1. Every value is at in t value 1. Okay. So we can easily write u1, and u1, u at 1 means u1 at 1 and u2 at 1. Okay. So clearly u1 1 is 1 and u2 1 is 2. So it will be a column vector of 1 2. So we can easily convert it into matrix form, and then we can solve it numerically or by analytical method.